So I'm going to be talking about the Memex, which is this amazing, cool concept from the past. And the paper is As We May Think. So who knows how to pronounce this guy's first name? Nobody? Okay, so it's Vannevar. I had to look that up. It's pretty tricky to find it out, but it's Vannevar Bush. And it was published in the Atlantic. So it's a bit weird. Like usually we're doing computer science papers, and this is a general purpose magazine. And it's nestled amongst "Forgive Me, Stranger," a poem, and "Birds of Midway" is over here. So this is kind of a general purpose, general audience essay. If you picked it up in the used bookstore, obviously you'd have no idea that one of the most important computer science papers is like kind of buried in this. Did anybody actually read the paper? Okay, cool. Yeah, that's right. This usually happens. I usually don't read the papers either. So but yeah, and if you read it, you would probably it's pretty dry. And Vannevar Bush was usually writing memos in his lifetime, so he's not really the best writer. But nevertheless, it's an amazing document.
And it's 70 years ago.
And it's really old. It's 1945. Yeah, so it's cool for that reason. And in this essay, he describes this device called the Memex. And the idea is that you put your whole library into this box, and you could easily look up stuff, archive stuff, make notes, make links, and the links become really important later on. We'll get into that. But it's this device to help you organize your brain. Pop quiz: how many of these were built? Zero. Yeah, it was a conceptual device. He kind of wrote about it, and that was that. So we'll explore that next. So just a warning, first of all. Oh yeah, one ahead. A warning. So there's lots of black and white photos. This is like a lot of history, and there are technical bits, but it is definitely about computer science, and it's definitely technical. But I think it's really more of a historical and cultural paper and talk. So and it's pretty interesting. I think you'll come away hopefully with some ideas for the future. So here's the outline. We're going to look at what computers were like before 1945 when Vannevar Bush wrote this paper. We're going to look at the article itself. And finally, we're going to look at what happened after, and especially this concept of an image of potentiality. So, concept that we all kind of think about now. Okay, so brief history of computers. So in an interview, Douglas Engelbart was talking about what computers were in the 1940s. And he said, well, basically it was a room of women, underpaid usually, doing calculations. And you'd ask one of them, what's your job? And they said, oh, I'm a computer. So this was computers. And this is what a computer looked like in the 1940s. You can see everybody's lined up doing hand calculations. This is one of my favorite pictures. It's another computer. It's actually the computing section of the computing division. And this is a computer. So this was state of the art. And this was just what we as a society had in the 30s and 40s. But around this time, we started developing these things called analog computers. And generally, in science and technology and engineering, we're concerned with one thing in particular, which is calculus. And in particular, we're concerned about this, which is the integrals. And it's pretty hard to do. I can attest to that. I got 50% on the dot in my first year of calculus class, which I think was a mercy pass. So it's really hard. Like I can definitely talk to you about how hard it is. So there's a long history in computer science and engineering about trying to make machines that do integration. And in the late 1800s, we already had the ability to do really simple integration. So this device was called a planimeter, and you basically take this tracer arm, you'd move it around the curve, and then with a cool bunch of things inside the machine, you'd get a number, which was the area inside the shape. So this is a really simple way to do integration. Around the same time, we figured out another cool technique, which is it's called an integrator, like a disk and wheel integrator. So there's two inputs here. So this is rotating at a fixed rate. We have a wheel on here which is connected to the spinning disk, and with friction, the wheel here is turning. And the speed of the wheel really depends on how far away it is from the center. And in the middle, it's not going too fast. At the edge, it's going a lot faster. And it turns out that if you move this whole arm back and forth like this, it is the integral of. You can calculate the integral. So so what you're doing is you're turning this at a constant speed, which is usually something like time, and you're moving this back and forth. And with this, you can do really cool integrals. Like it's a really elegant way of doing it. And Lord Kelvin turned this technique into a giant device to calculate tides. And he used a variant on it. Instead of a disk, he used a ball, but it's the same principle basically. You're moving time at a fixed rate, and you're moving an arm back and forth, and you get the intervals. So that's cool. This is kind of like what existed in the early 1900s and late 1800s, and this is kind of state of the art. And you could have a few specific applications, but generally there was no general purpose computing. So at this point, we're going to talk about our friend Vannevar Bush. These were his dates, and he was born in Massachusetts. He was a tinker and engineer right from the beginning. He was like always fidgeting with stuff, building cool inventions. This was his master project. Sorry for the really grainy photo, but it's called the profile tracer. And what you do is you take this bike-like thing and you roll it up and down the hills, and you get you figure out what the planes and the angles of the ground are. And inside the box, here's another example, is the disk and wheel integrator that we talked about earlier, and the output of it is literally plotted on a piece of paper. So this was kind of like this was what computers were like in the early 1900s. And he got to thinking about this. He was in MIT, and this was his master's research, and he kept thinking about this. And he was like, we can do better than just doing simple bicycle machines. So let's have a look again at our integrator here. So with a lot of complicated math equations, we can use differential equations to solve them. And differential equations are where you take the derivative of one equation and you pass the result back into the second one, and you just keep on feeding derivatives into the next equation. So I mean, in theory, you can take a bunch of these integrator machines and chain them one after the other and really solve complex equations. But there's one mechanical problem. It's not a theoretical problem, it's a mechanical problem. So let's think about it. If we're turning this, and then we're using friction on this wheel here to get the derivative, and then using this output to drive another integrator, what's the problem?
Okay, loss from friction.
Yeah, so loss from friction, that was a big one. Yeah, and the other problem is torque. So this shaft here doesn't drive enough torque to power the next integrator. So this is like a big problem, and it really limited what we could do with these analog computers. And Vannevar Bush, this is sorry, I'm getting ahead of myself. So in theory, we would want to string along these integrators, pass them along into the next one, and then take the plot of the output. And yeah, the torque is a problem. So what Vannevar Bush figured out how to do is take another device, which is a torque amplifier, and basically the actual torque is connected to a motor, but only at a specific time when the rotation is happening. So this way you can take a really low torque turn and amplify it. And this wasn't his own device. He just kind of combined it with the idea. And it's pretty cool if you it's a bit hard to explain because the diagram's bad, but it's a cool, elegant way to get torque out of a shaft. So it worked, and they were able to build these amazing, complicated devices, and you can see how many integrators are chained one after each other. And this was programming in the 30s. Programming was about figuring out how to set up your differential equation. So it's a series of integrators. And then there's also special things you can do to the torque, to the turns, to let's say add two numbers, or do like a subtraction or a factor. So this was kind of like what we could do. This was state of the art. And here's an example of the machine. And the coolest thing about it, I think, is that it literally is just paper. It's inputting a curve, the machine doing a bunch of things, and then plotting the output on a piece of paper. And this machine was a big deal. This was like the best computer we could find. People were talking about it. It brought a whole bunch of prestige and money to MIT and to America even. This was like a real landmark. This is another example of it in use. So you can see here, you're taking a curve, you're tracing along it. So that's what powers that first integrator. It goes through the shafts, and then on the other end, you're plotting a line, and that line usually represents the integral or the thing you're solving. Yeah.
And what did they actually use it for?
So the applications would be things like so the first major use was calculating. You have a network of transmission cables, like a phone system, and you have to figure out how much voltage to pass through the transmission cables, and that's a pretty hard integration problem. So you can set up an equation and do the calculations on how much power. So that was the first use, but it's a very you can pretty much break any problem down into a differential equation, and things like let's say tide calculations or ballistics, which ended up being a big use. These are classic problems. But yeah, they were big like calculating problems. Yeah. So and like the output is always just a curve on a graph. It's really simple. Like it's just taking the formula and doing a mechanical version of it. Yeah. So again, it's like it's huge, like really big, weighed a lot. But this was state of the art, and this was a big deal. Like people were talking about this, and you won all kinds of awards. Just as an aside, this amazing woman, Beatrice Helen Worsley, actually built one at U of T. And I was trying to, it was like a footnote I just came across, and I couldn't really find too much more about it. But we don't really know what happened to the machine, but apparently U of T used to have one of these, and it was built by her. Yeah, so I'd love to find out more, but I didn't have time. So yeah, back to Vannevar Bush. So the big thing was in the 30s, there was the lead up to World War II, and one of the problems is that gunners on boats had to figure out ballistics, and there's all kinds of variables. There's like the type of gun, the fuse type, the hardness of the ground. There's atmospheric pressure. There's even the rotation of the Earth, which as a shell is moving through the Earth, like that becomes a factor. And you can't obviously take this differential engine on a boat because it's too big. But what you could do is calculate all the permutations of the numbers and put them into a table and give those to the gunners. So these were the first like real uses of these things, and it was really important for the war. Like people really like think this is one of the reasons that America had an advantage during like technologically during the war. Yeah, and here's another picture. If your mind is thinking, oh, it's a whole bunch of shafts that are moving back and forth like this, your mind starts to wonder, couldn't this be done in binary? And this is a tangent. One of the students of Vannevar Bush who worked on these machines was, does anybody know the author of these two papers? Claude Shannon, yeah. So Claude Shannon like worked on these machines. He understood that you could pretty much break down any complicated problem into binary and then solve it as a binary system. And he wrote these two amazing papers, which are pretty much the foundation of computer science and computers generally, which we should do papers we love. Someone should do them because they're cool papers. But yeah, that's an aside. And he worked on Vannevar Bush's projects, and Vannevar Bush was a big like supporter of his work. But that's a tangent. Okay, so that's the first machine. It was called a Differential Analyzer, and it was a big deal. We're going to talk about a second machine that Vannevar Bush was involved with, and this is the comparator. Really good names in the 30s and 40s. And the problem is that we have a microfilm library, and this is like our haystack, and we want a needle, and that could be like a pattern or a title or something. We want to be able to search this collection really quickly. And the problem is that it was mostly a manual task before, and in the lead up to the war, the Navy wanted a faster way to do this, and it also had applications with cipher cracking, but that was secret until recently. So Vannevar Bush started thinking about it as a tinker and engineer, and he came up with this system. So next to the microfilm, you put a code, and then the operator puts a search card, and when you shine a light through the card, and it'll shine through the right pattern, a photocell goes off, and then mechanically you can do something. And usually that something was just projecting the result onto a screen or whatever. But the point is this helped reduce a manual task down to something that could be done really fast. And in this case, it could do 30,000 simple comparisons per minute, which for a mechanical device is pretty amazing. Like that was a real landmark. But it had a few problems. So first of all, microfilm breaks down when you're using it really fast. Paper breaks down when you use it really fast. So like this thing ended up not being too reliable. But then the bigger problem that Bush really struggled with is classification systems sucked. So if you have a big library and you're trying to search for something, you really have to guess what the librarian or what the person who coded the index card decided to put it in. And with a hierarchical system, you can only have it living in one category. And practically speaking, this meant that people couldn't find stuff very easily. So you had this cool mechanical system, but not a really good. It wasn't actually too useful. So Bush started thinking about that. Around the same time at MIT, this emerging field called cybernetics came about, and it's kind of a fuzzy field. The literal meaning is the study of self-government, and it was from Plato's time, and it was about politics really. But then it became adopted to biological systems, and scientists noticed that human brains and nervous systems work similar to computers or what mechanical systems, and the study of cybernetics was trying to compare them and link them together. And everybody at the time thought it was fuzzy, and that's kind of true. But it ended up being the foundation for AI. So in this sense, it was a big deal. But for Bush, when he looked at cybernetics, his takeaway was thinking about the brain like a machine. And in particular, he thought about how we recall memories, and it's not by looking at an alphabetized list; it's by association. So If I'm trying to recall a document, I'll remember it by who sent it to me or what it's about or like where I was even. And that's how the human brain recalls information. So that's what Bush was stewing on all this time. But generally speaking, Bush was a busy guy. He was a really good administrator, and his main role was managing science projects in the lead up to the war. And he became the president's like chief advisor, and he had like a whole bunch of projects under his belt. And you know, as he's you know, he becomes in the public eye through this, and Time magazine puts him on the front page in 1944. This was even before the war ended, and they called him the general of physics. As you know, he's another general in the war, and he's fighting the war on the science front. Like he was well known for at this time, and most of his time was managing these projects. But while he's managing these projects, he's encountering another problem, which is information overload. And he's seeing all these reports, he has all these scientists reporting to him, and he's really struggling to understand everything they're saying, and everybody's struggling to understand the amount of information. And this was like a really big problem in America in general. In the lead up to the war, all the bureaucracies that existed like just started ballooning in terms of information produced. So just as an example, the Office of Price Administration alone produced more paper per year than the entire government had before the war. So like there's this explosion of reports and documents and typed things. And Bush is really struggling, like, you know, we're so smart, but we don't have any way of dealing with this. So yeah, this is the backdrop, just to summarize again. We have a differential analyzer that proved computers could do stuff, you know, kind of show that they're useful. We have the rapid selector, which is at least a theoretical way of searching through a microfilm library really fast. We have cybernetics, which is starting to tell us about how human brains and computers can be similar. And then we have the problem information overload. But the most important thing is kind of not apparent yet. So the paper was written in July 1945. So what major world event happened 1 month later? July, so this would be August 1945. Yeah, so the atomic bombs were dropped. Like this was like, for people at the time and even for us, like this was like the most important thing that happened in their lifetimes, really. It was a game changer. And it's not like Vannevar Bush was a prophet and he knew that this would happen. It was because he actually worked in the Manhattan Project. So he was one of the secret directors of the whole project. And like, I guess as he's working on this, he's really struggling with the kind of ethical and the practical problems of having a tool that is this powerful. Yeah, so we have the bombs here. And I think especially he understood that, you know, we're losing our ability to understand the complexity of the world, but we're also gaining the power to blow ourselves up. So this is a pretty dangerous combination. So yeah, this is the backdrop for the paper, as we may think. And these are all the things that are kind of sitting in his head while he publishes the paper. And he put his thoughts together. A lot of them are pretty old, like they were from even 10 years before, but he writes them up in an essay and he submits it to the Atlantic. So at this point, we're going to now move to talking about the paper itself. So the way he introduces it is, he says the Memex is a future device for individual use. It's a mechanized private library, and you can put all your documents in it, and then it can be consulted at exceeding speed and flexibility, as all the language of the 30s and 40s. And the Memex was just an arbitrary name he came up with. People don't even know what it stands for, but probably it's memory extender. That's what it means. And here's a picture of it. You can see it has 2 screens, so it's kind of a dual monitor system. The microfilm is stored in here, and it's retrieved automatically and projected onto the screen. This is like the buttons to operate the thing, and the code book. So you type in a code and retrieve a document and show up here. And then this is an input device where you could write your notes and your annotations, and you could it would be kind of reproduced into microfilm and stored. So this was like the concept of it. It was yeah, basically 2 screens for microfilm and a way to, you know, manipulate and search and connect. Someone made a modern version of it just as another view. It's missing a lot of stuff, but you can kind of get the sense. Like it was a cabinet. That's like a desk. Like that's what the idea was. And here you can see like just a close up of like what the buttons might have been like. And this is just a graphic, and I'll walk you through a scenario he talks about in the paper. So he's describing this box, its capabilities, and then he talks about a use case, like, you know, it's kind of like a user story or something. So the owner of the Memex, let us say he's interested in the origin and properties of the bow and arrow. Specifically, he's studying why the Turkish bow was apparently superior to the English longbow in the skirmishes of the Crusades. he's very obsessed with bow and arrow. If you read the paper, it keeps coming. The Turkish bow keeps around. So he has dozens of possible pertinent books and articles in this Memex. So first he runs up an encyclopedia. So he gets in his code book. This is actually a paper notebook with codes and kind of like a lookup table. And he finds an encyclopedia and he puts it on. He types it in here, and it appears on the screen. Okay, so we got that. So he's reading through that. He can use this thing here as a scrubber to kind of move forward and backwards. And his mind gets to thinking, oh, this is the science of it. What about the history? So he pulls up his code book. He looks up a history book, and from the filing cabinet, it kind of automatically shows on the screen. And at this point, he has two different documents on the screen. And then, so what does this say? He finds a pertinent item and ties the two together. So this is the key. Instead of just looking up stuff in a linear process, he thought that the important thing was to be able to link together things. So if you have a history book and an encyclopedia on two screens, you can create a link. And it describes how you can keep on going through this process, and as you navigate, you're building a trail. And what it probably meant, like the actual implementation details, if we're interested in that, was adding codes to the side of the microfilm, and it's basically a linked list of pointers where you have like a trailhead. Let's say the Turkish bow is the trailhead. You can navigate down the trail and explore all the side trails. It's a linked list. And he goes on to, where's my cursor? So he builds a trail, and this is kind of the research process of the future he describes. And again, in the paper, it says, several years later, his mind turns once again to the Turkish bow in a conversation with a friend. He gets out his code book and he looks at the start of the trail, and he goes down the path with this and kind of talks to his friend through it. And then at the end of the process, he takes the whole trail and reproduces it and gives it on microfilm to his friend, and his friend loads it into his Memex. So this was kind of like the amazing device he comes up with to deal with information overload. And again, to summarize, he can summarize. It's wholly new forms of encyclopedias will appear, ready with a mesh of associated trails running through them. So it's kind of a new way of looking at information. Instead of being a kind of a hierarchy of book, table of contents, and then chapter, paragraph, it's thinking of information as a web. And he found this was a way to deal with information overload. And then he describes a few things that this thing will help people with. So it'll help lawyers, it'll help patent attorneys, doctors, chemists, and in all of these examples, it's not just as a way to look up existing material that they have already. It's a way to explore things that they've explored before. So like a chemist might walk over a path that they looked up 2 years ago, or a doctor might look up based on symptoms, like they'll encounter a trail that they had 5 years ago when they saw the symptoms again. So it's really a way of like almost re-accessing memories that you've had in the past. And then, interestingly enough, he started talking about a new class, a new profession, which would just be trailblazing. And this could be people who are really interested in the material, and they'll go around creating these trails and then maybe selling them or packaging them up and giving them to other people. So it's kind of like forward-looking that way. So the paper had a big impact. Life magazine picked up on this paper, and they kind of did a popular science version of it. And this version has a Cyclops camera here. As an input device, and it's kind of like, this is like a cheesier version of the paper, but I mean the concepts are still the same. This is a device that you speak into and write notes. Also, make sure to read the wonderful ads here. This is the best part of doing research as the advertisements, really. And then this is expanding the concept of how do you draw notes and how to link things together.
Hang on, what about the spanking children? Go ahead.
So the problem is that children don't go to the bathroom, so if you give them this good laxative, you won't have to spank them. Okay, so this is the wonderful 40s.
That's where my parents went wrong.
That's all I need to know.
Okay, so back to the Memex. So it came out in Life, and again everybody talked about it. And what happened next? BuzzFeed. Not too much actually happened. Like people read it, people talked about it, but in some ways it was a little bit too far out there for anything really to happen. And besides, Bush was pretty busy. Like he was involved in. He was a co-founder of Raytheon, which is a defense contractor. It still exists. And they service military contracts. He was involved in ARPA, which was like the American way of funding science and technology projects, which ended up creating the internet, by the way. But he was the manager of this organization, and he was a busy guy. Like his day-to-day was mostly taking care of these science projects. But he never stopped thinking about the Memex, and like as decades went by, he published another version of the Memex, and he updated it to reflect some of the newfangled technologies, including instead of microfilm, it was based on crystals, and crystals was like the persistence layer. I don't really understand, but that was his way of thinking of a better storage mechanism. He even hypothesized that computers could think and that we could communicate them with our brain because we can just put sensors on our brain and pick up signals. So it was kind of a ESP AI kind of system, and it's pretty far.
Things on crystals, like is that a real thing that you can do?
I don't know. Apparently, there's it's pretty primitive. I don't think he really understood if it would work or not. It was he was just throwing it out there. And I mean, I think the reason he's talking about crystals and not like digital computers is my next point, which was this. Which computer? Does anybody know which computer this is? It's the ENIAC, yeah. So this was the first digital computer, and it was huge again. But the key difference here is that it's not an analog machine that's cranking out lines on a graph. It's running binary calculations based on Claude Shannon's work, and kind of like it's like the same model that we use for computers today. And this came out in 1946. It was built just a bit too late for the war. But as soon as it came out, this was like the new way to do it. And Bush's analog computers like went to storage and like never again had their moment in the sun. And Bush was pretty bitter about this, and he never really understood these new digital computers. In fact, when he was running the science organizations that funded all these projects, he even tried to get the ENIAC defunded because he didn't think they were reliable. And in some ways, he was kind of right. Like it was pretty unreliable, and the vacuum tubes especially would break all the time. And you'd be lucky if you got like an hour of computation, and then the vacuum tube would break, and you'd have to do your whole operation again. So they were pretty horrible at the beginning, but this was the way of the future, and we all kind of understand why these are better than analog computers. Bush never understood these, and I think so. An author of a book I'm reading about this said binary electronics robbed him of the chance to watch a machine grinding out solutions, and he really liked that connection, the mechanical connection between a formula and the result. And binary computers were just these things that threw electricity signals through a circuit, and he didn't really understand the connection. So at this point, he just kind of steps back, and he's like, let the kids take care of the future. And he retires, and he has a happy retirement. He ends up taking care of a lot of turkeys, I think 700 turkeys. And he keeps inventing stuff. As he ages, he loses the ability to walk around too well, so he invents a chair for his bathtub. And like right before he died, he almost got this distributed in Sears, and he was really excited about this. So he was tinkering right to the end, and I think that's kind of where the Memex story ends in some ways, but it really doesn't, because here I am talking about it. So obviously something happened, and I think what happened is that people read this and took it and started doing stuff. So my favorite is Douglas Engelbart, who's like all around amazing guy, maybe the most important person in computer science history, in my opinion. And he worked on this project called the Augmenting the Human Intellect project, and it was a really big deal, and I'll get to why in the next. But first, World War II, and as all young men were in the era, he was part of the military, and he was part of the Navy. And he was an engineer and a tinkerer as well. He was really good with figuring out stuff and making stuff. And his job ended up being servicing radars. And he was really good at it. And at the time, it was a cathode ray tube, and something would be picked up, and an electron would shine it into the screen and light up on the screen. And his job was to fix these and understand them. Here's another example of a radar station at the time. But the problem is that he was deployed at the end of 1945, and the war was already over, but he was sent to the Philippines anyways. And there's nothing to do. He's bored out of his mind. And at the time, the Red Cross had set up a library in basically a hut like this. This might actually be the same hut, but we don't know for sure. They set up a library, and they brought a whole bunch of books over to the Philippines for their bored soldiers. And Doug Engelbart stumbles into this library, and inside is the Atlantic magazine, which has the Memex article. And he reads this, and he's just floored. He'd never understood computers this way. Like, it gives him a whole purpose in life. Like, he always talks about this single event in his life as being like the origin stories of everything he does. And it's actually cool. Like, on his website, you can see this is his annotated copy. You can see all his marginalia, and like you can really pick up how excited he was about this paper. So he read it and digested it and kind of came out with these 3 goals for himself. Premises. First of all, as Bush was arguing, we've kind of lost the ability to understand complexity. Secondly, Doug, he's talking about himself, could make a difference in the world by building tools to make people smarter. And this became his mission. And in particular, he thought forward to the future and thought that computers could be interactive like the radar screens, and you could have an operator sitting at a table doing stuff and getting responses right away on the screen the same way the radar had. And that gave him purpose, and this was his goal in life now. The problem was that he was stuck in kind of like mediocre jobs and he wasn't doing too well, and then he ended up in California. This is all when everything began to click, and I think a lot of people try to wonder, what was wrong with the East Coast where he was based and what was different about California. And in a lot of ways it comes down to this. And LSD was, it was actually literally used by everybody in California. But it was kind of representative of what was going on in California. And so LSD in particular, there was a few researchers, and they discovered this stuff in the early 60s, and they just systematically and scientifically experimented on everybody. And it wasn't just like a party drug. They guided people through a process of exploration and discovery. And pretty much every researcher and science person in California had gone through an LSD experience, including Doug Engelbart, and everybody had good experiences. And everybody was thinking about the universe and big pictures and kind of how to change the world. And back on the East Coast, things were very conservative, very hierarchical, and especially the computing culture. It was very much about big computers and air-conditioned rooms with kind of like guarded by operators. And California was kind of a land of hope. So Doug Engelbart lands in Stanford. This is not him, sorry, this is kind of misleading. This is not him, this is the only picture I could find of SRI. So he comes into Stanford, and he puts to work, getting to work on this kind of Memex goal of his. And he assembles a team of cool, young, hip people, and they begin working on computer systems that could help individuals and make people smarter. And the whole thesis of this project in the group was that the tools we use actually co-evolve with us as humans. So, like our language systems, for instance, actually shape our brain and make us smarter in a particular way. And if we want to make humans smarter in the future, it's about finding tools that will empower us, change the way of thinking, and will actually co-evolve with these tools. And one of the things he did early on was kind of prove the opposite, and it's what happens if we downgrade our tools. So what he did is he took a brick and strapped it to a pencil. And you can kind of guess what happened. Obviously people didn't do too well on this experiment. And he uses, it's like, look, if we downgrade our tools, we're gonna stop being able to think this way and write this way. Obviously, if we go the other direction, we'll get a lot smarter. So this was the whole augmentation hypothesis that he was working on. And they didn't know exactly what they were going to build. They wanted to build interactive computing in a way that people could talk to each other, but they didn't quite know what they were doing. And instead they kind of used a process that we call, I guess, lean or agile now, but at the time we called it bootstrapping, or eating his own dog food. And the team kind of built internal tools, and the whole project was, they all did it on their own software. So they built a messaging system, they built like wikis, all the documentation for the code was interactive and you could jump around in it. You could kind of leave timestamp comments everywhere. It was like really ahead of its time. There's features in here that are like still not really implemented properly. It was a super creative time. Remember, computers are still pretty big and you can't do too much, but they still found a way to, do a computer run meeting. And here they've created a special U-shaped table where they can bring their displays into the middle, and they run their computers they run their meetings almost like the same way we would today. Obviously, because it's California, they also this kind of experimental stuff. So this is their yoga workstation. And instead of a standing desk, they had a sitting desk. And it was a very experimental time. And a lot got done. It was very productive for everybody. And at the heart of it, so they called this system that they were building the online system, and they named it NLS. I don't know why they didn't have the O, but it was called NLS. And at the heart of it was this idea that linking is a first-class citizen. So everything, whether it was documentation, whether it was an email message, whether it was like a document, everything was able to be linked. And there was even linking within documents, so you could that's something that's still pretty hard to do in HTML, but this worked in NLS. And yeah, the hunch was that the links between our information are sometimes more important than the information themselves, and that was the big thrust of this project. And again, the other thing that came from Bush was this idea that computers shouldn't be these big boxes for calculating bullet trajectories. They should be for individuals. So they came up with new input devices, which is where the mouse got invented. And this is a one-handed keyboard, and it's actually pretty cool. Like, people in his lab could type faster than on a keyboard, and you do it by combining characters. Unfortunately, this one picked up and this one didn't. But these were two input devices that were like kind of changed the way we use computers. And incidentally, this whole concept was based around the disk integrators that people knew about in the 20s that Vannevar Bush had worked on. So it's kind of a nice circle. But yeah, like, there was a direct link between those early integrators and the mouse. Like, people just thought of the same idea. Yeah, and this was again a picture of the station. I took this at the Computer History Museum, and you should go have a look at it. It's pretty awesome in California. But the whole problem is that that Engelbart had a lot of trouble explaining what he was doing. It was like a big kind of pie in the sky California concept. In fact, like, he had to almost hide what he was doing from like the East Coast funders who were giving him money, and he kind of pretended that they were working on like military technology, but really they were working on a secret project. But he really wanted a way to explain this to people. So they did a Hail Mary, which was a big presentation where they devoted like almost a year's worth of their budget to setting up. So it was a joint, I think it was the ACM or like one of the early computing societies in California and San Francisco. It was a 1,000-person room, and Doug Engelbart set up a demo at the front, and like everything about this was like revolutionary. Like, even the fact that they had a projector screen, like this didn't exist at the time. They had to rent a special device, and it was based on oil and electrons, and it was just weird. Like, none of this was easy. And he sat up there and did a demo. And this is kind of this was, unfortunately, there's no pictures of him actually doing the demo, but this is of the practice. So he sat at this terminal with the mouse. They set up a whole bunch of cameras, and he had a headset on. And he basically used the online system for an hour and a half and just did things. And he was like, okay, I'm going to work on a document now. And he opened it. And you can kind of see that this is like a still from the actual, this would have been on the big screen. And he just walked people through what using a modern hypertext system was like. And it was amazing. It showed a whole bunch of things that people hadn't seen before, including the mouse, group messaging, like a form of wikis, like email, hyperlinks, as we talked about earlier, video conferencing. At one point, they set up a microwave link between their Menlo Park office and San Francisco, and they just beamed another person from the lab onto the screen. And like, nobody had ever seen this. Like, you can hear the gasp in the audience when this happens. Like, nobody had ever seen this before. And actually, most interesting, like to me when I was reading this, it was the first software engineering, because before there was kind of a lot of ad hoc programming, but because there was a group of 10 people working on a software project together, they had to figure out like conflicts and merges and bug reports and documentation for the first time. So in some ways, this was like one of the first software engineering projects. So yeah, this was like an amazing event, 1968. It's totally worth watching on YouTube. It's like worth every of the 90 minutes it is. And Engelbart was pretty proud of it. And at one point he was like, I should see if Vannevar Bush is still around and wants to talk about this. So he wrote him a letter. And it's like, if you still have interest in this area, I'll send you a copy. And he didn't think anything of it. He actually assumed Vannevar Bush was in an old people's home, like he said in an interview later on. And it turns out he was alive and healthy and still publishing, but like, because the internet didn't exist yet, there was no really good way of talking to each other. So that connection just never really happened, unfortunately, and I wish it did, but it didn't. So that's kind of the end of the Doug Engelbart story, except for a lot of the ideas he had ended up in Xerox PARC, and kind of sad for him, but a lot of his best team members ended up getting poached to Xerox PARC, and then from there a lot of the ideas disseminated into like the modern PCs. So that's one kind of person that Vannevar Bush's Memex paper had like a really direct, clear link to. Another was Eugene Garfield. So he read the Memex paper, and his takeaway was more about the links and organizing information that way. I mean, yeah, same with Engelbart, but he had a different angle on it. And he looked at academic research, and he's like, we can figure out who's influential in the field by treating citations as links. So what did he do? So he looked at all the academic research. He figured out who was mentioning who, and he made a graph out of it. And you can see, like, for instance, this is like obviously a very important paper because it's mentioned by a whole bunch of people here. And this became citation analysis, and he built the first citation index in 1955. And if you're looking at this kind of concept of pointers to papers, what does it look like? What kind of algorithm do we know about now? but more. If we take this concept and put it on the internet, what does it become? PageRank, yeah. So this had like a direct. This work that Garfield did had a direct link on these two guys who built Google, and like if you read the original PageRank paper, it's like completely based on Garfield's work. So it's another cool connection that Vannevar Bush has. And then the final person we're going to look at, kind of like the spiritual descendants of Vannevar Bush, is this guy. Everybody know who he is? Ted Nelson, yeah. So he's an incredible thinker. He was not really a technical guy, but he was a dabbler. He dabbled in everything, including like dolphin research and film plays. And then in the 70s, he discovered computers. And he's kind of all over the place. An author that I just finished reading called him the Don Quixote of computing, because he'd come up with these crazy concepts and then get obsessed about them and then frustrated when nobody implemented them. So this is him as a character. So in the 70s, very early 70s, he saw computers for the first time. He's like, holy shit, these things are important, but they're too important to be left to computer operators in big rooms. So he wrote this zine called Computer Lib. It's so cool. This is like the coolest thing you can find. You can and must understand computers now was his tagline. And he self-published this. Nobody would take a chance on it, so he self-published. And it's this crazy book. Like, it's all hand-drawn. It is a zine. Like, these are all like done by him. He's like, what are computers? He goes over them. And his hypothesis was that computer prices are falling, and you better learn these things before they become important and they leave you behind. So he explained, where they are in the States. This is his handwriting. Where computers are. He has this is like a programming tutorial. With, this is a pointer demonstration. This is a APL programming language tutorial. It's really good stuff. He even has, this is the problem of, if you're learning computers for the first time, obviously the more experienced people are going to put you down and tell you to get out of here. So here are some comebacks he gives you that you can like launch at people if someone's telling you that you don't belong, including, oh yeah, how about the X work using A? And like he says it doesn't matter what numbers you use, it'll just shut up someone. So kind of understands the cultural kind of impact of computing. But the coolest thing about Computer Lib was that it was actually a 2-in-1, and if you turn the book over, that became a second book called Dream Machines. And in my opinion, this is like the better of the book, better machines. And Computer Lib is all about teaching computers and explaining what they are, and Dream Machines is all about teaching people how cool computers could be and what's coming in the future. So here's a page explaining, this is about games. This is about early computer graphics, and he's just he's just scrawling on a piece of paper explaining how these things work. But it's really good. Like, it's actually clear descriptions of everything. This is an explanation of interacting for computing, and this was like a bible in early hacker culture. Like, people traded these copies. It was like everybody was reading this, including these guys who are the Homebrew Computing Club, and this came about in the early 70s as well. And this was like the Computer Lib was the book that these guys read. And when everybody started building computers for the first time, they were kind of reading Ted Nelson at the same time, and including these two guys, Wozniak and Steve Jobs, and they cleaned up a little bit and they built the first Apple. But yeah, like this is coming out of Ted Nelson's kind of culture and the early hacker culture. But really, Ted Nelson cared about one thing, which was the Xanadu project, and this is kind of where it gets interesting, I guess, from a hypertext point of view. And some people have called this the longest running vaporware project in history. He actually started working on this in like the mid 60s, and he's still working on it today. Like, he's alive and well and working on the Xanadu project. And it came out of the Vannevar Bush hypertext idea, and it was kind of a more complicated version of hyperlinks. And Ted Nelson's obsession was with two-way links. So instead of if I link something on a website, that source could go down and the link is gone. Whereas with Xanadu, there was two-way links, and the actual material would be transcluded, that was his term for it, in the source document. So there was a kind of a two-way linking. And obviously he felt that this is like, the best thing in the world and everybody should be using it. And he's really bitter about the fact that we're not, but he keeps working on this. This is a version from the 90s. And he's really proud of this, and he thinks this is incredible. I think it's a bit hard to use. A few years ago, he actually announced that he was releasing the first beta version of Xanadu, and you can go on the website and try it out. So I did. This is what it looks like. It really doesn't work. So just in terms of JavaScript, they're loading each of these pages into memory, and like you're trying to scroll, and it just doesn't work. But he's really proud of this, and he feels this is like an important step in the Xanadu project. But he keeps cranking out the code and working on it, but it's not really getting anywhere. But it doesn't really matter because the ideas that were in Xanadu have been like taken by everybody, and like for instance, Tim Berners-Lee, when he invented the first browser, was completely modeling it on the Xanadu material. And Ted Nelson would argue, oh, he got it all wrong and he didn't do links properly. But I mean, in some ways, we got a version of the internet that works instead of. So yeah, that's kind of what Ted Nelson's contribution. And you know, he did pay respect to Vannevar Bush. He gave him a little section in the zine. But of course, he says, you know, everybody gets it wrong about the Memex paper. I'm the only one who understands it. So in the mid '60s, he calls Vannevar Bush up, and he tells him about the Xanadu project, and he tries to get him on board. And then he changes his mind. And an author of a book I read had a really good reason why he changed his mind. It's like Ted Nelson's like, he sounded like a sports coach. And I think that was his way of sounding. Like, you know, Vannevar Bush was obviously in his 60s, 70s, he was aging, and he just wasn't hip like Ted Nelson. So Ted Nelson never talked to him again, and that was kind of like the end of the link. But I mean, these are all kind of offshoots of that original Memex paper. So to conclude, like obviously I'm talking a lot about like kind of the spiritual history of this paper, and like everybody agrees. Like this is like a random tree I found on the internet. Like, you know, it's tracing either Windows CE back, you know, to the Memex. And there's a lot of like talk in the computing world about how everything started at the Memex, and it's kind of true. Someone did a citation analysis in the early 90s, but it's still pretty relevant today. Linda Smith, and she found that there's 375 citations, academic citations, in the 45 years between it was published. Like, there is almost complete agreement that this was an important paper. Everybody talks about it as being foundational. But like all of us who didn't actually read the paper today, it seems that a lot of people didn't actually read the Memex paper, and she goes through kind of like the way it's used, and like she argues that most people didn't really understand kind of like the nature of links and the nature of associated linking. And instead what the Memex gave us was not the specifics about how a Turkish bow could be looked up in associated links. It was an image of potentiality, and this is the phrase she uses. And it's this idea of a vision of what computers could be like. And I think sometimes as engineers we get really, you know, we kind of look down on prophesiers and prophets, I guess is the term, prophets, and we look down on kind of the fuzzier side. But it's really important, I think, and there was a symposium in 1995 about Vannevar Bush, and a lot of the, you know, people influenced by him showed up, and one of the people was Alan Kay, and this was his closing thought about it. So he's talking about computing history, and he's saying, nobody was a computer science back then, and he makes the argument that the reason everybody was so free to do crazy things was because there weren't really categories and labels, and people really felt free to pull in ideas from other places. And then he says, engineering is one of the hardest fields to be creative in, just because it's all about optimizing. And sometimes you need like a complete rotation of a point of view. And I think that's like a really important thought, and especially like if we had only focused on optimizing computers, we would have got a lot more like this. Which is, you know, computers as giant calculators, which did things like ballistic projections or payroll, and it was computers guarded by a cult of priests who didn't let anybody, you know, touch their computer, and again, computers serving institutions and not individuals. And the importance of the Memex paper is that it gave us a completely different idea of what a computer could do. And I think that's like my takeaway from all this is sometimes like the vision itself is bigger than the specifics. Especially if the specifics involve like Cyclops cameras. So, yeah, so that's the paper. I'll just jump to this for a sec. If you're interested in this topic, which I've had a lot of fun exploring, I think you should all too. Watch the mother of all demos. It's on YouTube. It's really good. It's from the late 60s, and every minute of it is like, it's like, why don't we have this now? And like that's a really cool feeling to have when you're watching something from the 60s. Acquire a copy of Computer Lib Dream Machines. So it's really hard to find in print. It's like a couple $100 if you buy it on Amazon. But sometimes if you type a book name and PDF into Google, like you find it somehow. So like I recommend trying to find it that way. There's a book that's kind of like the cultural history of computers at times, so what the Dormouse said. It's about early hacker culture and kind of like the California experience. And then if you're in California, go to the Computer History Museum, because a lot of these machines are there. A lot of them work actually. Like it's really cool to see like a computer from the 50s or 60s work. And it's like they have a really good, like everything's well labeled and everything's really well funded because it's tech money. So it's like a really good museum. It's right next to Google, so I recommend visiting.
You can borrow the Google bikes.
Yeah, you can take the bike and go across the street to the museum. Yeah. So that's the Memex. Any questions or comments? Okay.
Does we make the slides available on the meetup page?
Yeah, I guess I should. Okay, I will. Yeah, I will have to add image credits, but yeah, I'll do that after. Yeah. Hey.
Just curious, is he connected to the Bush family?
I don't think so. I don't know. That's a good question. I don't know why.
Thinking about the heritage and
Yeah,
defense.
I mean, it was a wealthy family from Massachusetts, so probably like way back. Yeah.
So the 41st president was from Massachusetts.
Oh, sorry. What's that?
The 41st president was from Massachusetts.
Yeah. So yeah, I guess there's probably a connection. I didn't see it mentioned in any of the articles I read.
I mean, by the time he was writing this, electronically limited digital electromechanical stuff was around, sort of like telephone relays and that.
Yeah.
But it's very focused on microfilm and crazy cyborg Cyclops camera.
Yeah.
Did he have a particular background towards that, or was this just
Like he was an engineer.
he saw the electrical side of things?
Yeah, like I think he was first and foremost an engineer, like a mechanical engineer, and like being an engineer at MIT in the 30s was about like building like mechanical devices, and I think that's the way he understood the world. And like even like a lot of the relays and stuff that were around the time, like that wasn't even really his world. He was more interested in like mechanical systems. Anybody else? Yeah.
So what got you into this? Interested in this?
Well, probably should ask. I'm working on a side project at the moment, which is a kind of a Memex, I guess you could say. And I guess when I encountered the topic, it appeals to us, like this idea that we can search our history and search everything we've encountered. So I think like all good computer geeks, I'm trying to build up my own. And like as I build my system, I keep going back into the history and like discovering cool things that really haven't really come out in our modern era. So I guess I'm building a Memex and reading about it at the same time, and it's a lot of fun. And yeah, I mean, even if you're not building a Memex, I'd recommend reading this paper and reading the history around it. Cool. Anybody else? Awesome. Okay, thanks everybody.